Hi, this is Mrs. Kidman, and in this video, we are going to be discussing similar polygons. So what does it mean for polygons to be similar? Well, similar polygons are polygons that have the same shape, meaning the same number of sides. Their angles are the same. Their angles are actually going to be congruent or equivalent in measure. So congruent angles and proportional sides. So what does that look like? Well, when we're looking at something like these two triangles here, we know that they're the same shape because they're both triangles. But how do we know that they're actually similar? Well, what happens is these angles here actually need to be the same measurements. Now, they don't all three have to be the same measurement, but you have to have congruent angles for the corresponding parts of those triangles. So if A is the same as D, then that means angle A needs to be congruent to angle D. That means that angle B needs to be congruent to angle E, and angle C needs to be congruent to angle F, right? So by knowing those things, that's one thing that's in common about these similar polygons. The other thing about those similar polygons is that they have proportional sides. Now, what does that mean when we talk about proportional sides? Well, what that means is that when we look at the ratios of the sides that correspond to one another, that ratio is going to be the same regardless of the side. So let's take remember when we were doing dilations, how we'd always do new over old? That's what I'm going to do here, is I'm going to look at the new versus the old. So that means that the ratio of DF over AC needs to be the same. Sorry, that C is a little messed up there. DF over AC. C, oh my goodness, AC needs to equal, sorry about that, the same as DE over AB, which needs to be the same as EF over BC. Now notice how those corresponding points are corresponded in these statements. Now the ratios of the corresponding sides actually all need to be equal, and they need to be equal to this point K, which is actually our scale factor. So remember when we learned about dilations, we talked about a scale factor, and that's how we determine how big or small something is. Well, when it comes to similar polygons, what we do is we actually look at those corresponding sides and determine their ratio. And that ratio is actually going to be the same regardless of what the shape looks like. And that ratio is what we call the scale factor. So the cool thing about similar polygons is we can use these different characteristics to find different things. And once we know these characteristics, we can actually show that polygons are similar, as long as we've shown that they have this, as long as we can see they have the same shape and show that the angles are the same and the sides are proportional. So let's take a look at a couple of examples here. First, let's start with this one. So in the diagram, our triangle RST is similar to triangle XYZ. So when we talk about similarity, I'll put it back on this page here. When we talk about similar polygons, we actually use this notation here. So triangle ABC, if it's similar to triangle DEF, what we use is, remember the congruent symbol is a squiggle over an equals. The similarity symbol is actually just that squiggle. So an equal means the same. Congruent means, or equal means the same in measure. Congruent means exactly the same. And similar means that they have a lot of the same characteristics, but they're not exactly equal. So it's kind of a cool thing to see similar plus equal equals, similar plus equal becomes congruent. Awesome, right? Looking just like those symbols. So let's take a look at this problem here. So we know that this first triangle is similar to the second triangle there, XYZ. So what we want to do is find the scale factor from RST to triangle XYZ. So that scale factor is that K. So what we want to do is we want to write these as proportions. Now, again, like we said before, we usually like to do new over old. So I'm going to do the new side versus the old side, and we're going to write them in those proportions. So I'm going to start with RS, which is 20, over XY, which is 12. And that should be equal to YZ, which is 18. This is reversed, sorry. We are gonna do our new one, which is XY. So our 12 over our 20, sorry. And then our 18 over our 30. And then lastly, our 15 over 25. Notice how these are in corresponding parts. Now, as we simplify these, they should all be equal to show that they're similar. And so what happens when we simplify 12 over 20? Well, a number that goes both into 12 and 20 is 4. And as we simplify that, we end up getting 3 over 5. 18 and 30 both have 6 in common, and that'll also give us a 3 over 5. and 5 over 20, 15 and 25 have 5 in common, which will also give us a 3 over 5. So our scale factor here is going to be that 3 out of 5 because all of those simplify to it. Now what we want to do is list the pairs of congruent angles. Now remember, congruent angles are in the same location. And so in this case, we've got angle R is congruent to angle X, angle S is congruent to angle Y, and angle T is congruent to angle Z. Then lastly, what we want to do is write the ratios of the corresponding sides in a statement of proportionality. Well, guess what? In part A here where we wrote this, that is actually a statement of proportionality. The only thing we have to tack on is that scale factor at the end. So to find that scale factor, we do have to compare all of those. So using those corresponding sides, we can write a statement of proportionality saying that even though these sides have different lengths, they're all directly proportional of a scale factor of 3/5. How cool is that? So let's take a look at this next example here, where we actually use these properties to determine what different side lengths are. So being told that triangle DEF is similar to triangle MNP, we've learned a couple things. We know that these angles here are actually all going to be the same as one another. That's one piece of information they tell us. And then they tell us that the ratios should all be the same. So if we want to figure out what this value of X is here, what we can do is we know that the ratio of 30 and X should be the same as the ratio of 24 and 20, or 18 and 15. So let's figure out what that scale factor is. And then once we have that scale factor, we can multiply it by 30 to go back here. So I'm going to treat this one as my original and this one as my new. So let's look at that proportion there. So we've got a 20 over 24 should be the same as a 15 over 18. Well, looking at that common factor there, these two have a common factor of 4, so that is 5/6. These two have a common factor of 3, which also gives us 5/6. So that means that whatever number we have here should be X over 30, where we end up with this ratio of 5/6. So 6 times 5 equals 30. So that means that X needs to equal 25 so that that ratio of 25 over 30 can simplify into this. So do you see what we did there? We looked at those and we know that this needs to be the same as this rate change. So we know X over 30 needs to equal 5 over 6. Now I looked at a process of saying what number can I multiply 6 by to become 30. You also could cross multiply and then divide. Both of those are great options depending on what you want to do. Let's take a look at one more example here where we use this property and this idea of similar polygons together. So in this diagram, we know that these two triangles are similar. So we want to find the length of the altitude PS. Now remember, the altitude of a triangle is its height. So what we want to do is find that distance PS. Well, we know that these two triangles are actually similar. So when we talk about the triangles, we're talking about this triangle PRS and the triangle XPZ. So if they're similar, what that means is that this length is similar to this length, and this length is similar to this length. And then we can use that proportionality to then determine what this is, because those altitudes should also be proportional. So if I know that this distance here, or that T to R, is 12, and I know that this distance from X to Z is 16, I know that we can find that ratio there. So 12 over 16, well, what does that simplify to? Well, 12 over 16, 4 goes into both of them, so we've got a 3 over 4. So triangle TPR is 3/4 the size of triangle XPZ. Now, how can we figure out what PS is? Well, to find the distance of that length PS there, what we can do is we know that it's going to have the ratio, it's going to equal this, or it's going to be in the ratio of PS over 20 needs to equal 3 over 4. So I'm going to use that same method where I ask myself, what can I multiply this by to get that? And I know 4 times 5 equals 20. So because I'm multiplying it by a special form of 1, because this is just another way to rewrite that fraction 3/4, I'm going to also multiply this by 5, and we get 15. So that means that length PS equals 15. Okay, isn't that cool how we can use these properties of similar polygons to find that? Now this applies not only to triangles, but any type of polygon that we want. So the next one that we're going to look at is we actually can find some other cool things by looking at similar polygons. For example, one of those is the perimeter of a similar polygon. So when we talk about the perimeter of a similar polygon, they actually have a really cool property. So remember, the perimeter is the sum of the sides. So if we take the perimeter of the new, which in this case, let's look at an example here with numbers. So let's look at these two here. What this tells me is the perimeter of the new divided by the perimeter of the old should be equal to any of the sides. So if this one, so let's take a look at these examples here. So if we have the perimeter of triangle ABC divided by the perimeter of triangle DEF, then that should equal that proportion of AB over DE, or that proportion of BC over EF, or that one of AC over DF. And the name for this proportion here is also our scale factor. So the perimeter actually is the same as our scale factor if we look at the ratio of those perimeters. So let's actually look at an example here of one like this one. So the town plans on building a new swimming pool, an Olympic, actually, let's not look at that one. Let's look at this one. So instead of, maybe not this one, we'll stick with this one. Okay, so the town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. The new pool will be similar in shape to an Olympic pool, but will have a length of 40 meters. So find the perimeter of an Olympic pool and the new pool. Okay, here we go. So to find the perimeters of the Olympic pool and the new pool, here's what we're gonna do. The perimeter of the Olympic pool, well, this is a rectangle, so it's 50 and 25. So we know that as we add these together, that the perimeter of the Olympic pool is going to equal 150 meters. Great. Now to find that perimeter of the new pool, what we're going to have to do is look at that proportion, because remember, we established that the proportion between the two shapes is going to be the same as the proportion between the sides. So in this one, we had a 50 by 25 rectangular thing, but we were told that the new pool is only going to be 40 meters in length instead of 50. So that means that we've got this ratio of the Olympic pool being 50 over the new pool, which is 40. And that ratio is actually a 5-to-4 ratio. So in order for us to get a 5-to-4 ratio here, we need to figure out what the perimeter of that pool is. So to find the perimeter of that new pool, if it's in a 5-to-4 ratio, well, 5 times 30 equals 150. So we need to multiply both parts by 30, and that's actually going to give us 120 meters. So the perimeter of our new one will be 120. The perimeter of our old one will be 150. And we know that because their ratio has to be the same as the scale factor. How awesome is that? So again, if we're finding the perimeter of a similar polygon, their proportions of the perimeters are going to be the same as the scale factor or the proportion of the sides. The last one that we want to talk about is actually the area of similar polygons. And so when we talk about the area of similar polygons, they actually also follow a relationship. So if the sides are proportional, the areas are actually proportional by the scale factor squared. So what does that mean? If I have the area of triangle ABC divided by the area of triangle DEF, what that actually ends up being is it's going to be the proportion of AB over DE squared. Okay, now area is a square measurement, so it makes sense that this scale factor is going to be squared, but it actually plays a huge role there. So as we're looking at these areas, we can see that it takes that into account. And this AB and DE, remember, that's the exact same as that ratio of BC over EF squared or of AC over DF squared. Okay, so that proportion of the sides squared is going to be the proportion of the areas. So let's take a look at these two examples here. So in the diagram, triangle ABC is similar to triangle DEF. We want to find the area of triangle DEF. So how can we find that area? Well, an easy thing for us to do is we can use this area and we can use the two sides that we have to be a proportion. So I know that the area of triangle ABC over the area of triangle DEF is going to be directly proportional to the sides squared. So ABC goes on top, so AB is the same as DE. Those two sides are corresponding in these similar triangles. So that's going to be the same as 10 over 5. But remember, because it's area, we're going to square it. So the area of ABC over the area of DEF is going to be equal to this proportion, which is squared. Well, that proportion there is actually a proportion of 2. And so what that means is that ABC is 2 times bigger, or that scale factor is 2 than DEF, right? So that scale factor there is going to be 2. And so because this simplifies to a 2, it's actually a 4. So what that means is the proportion of the area of ABC over the area of DEF needs to equal 4. So how can we decide what that is? Well, we know that the area of ABC is 36. So 36 over something needs to equal 4. Now we can solve for this 2 different ways. We can either come up with a number 36 divides by to get 4, or we can multiply both sides by x and get 36 equals 4x, and then divide both sides by 4. Either way, what we're going to end up getting is that x equals 9 centimeters squared. So we can use this idea of this property of the area of similar polygons to see that that proportion helps us when we know the area of one thing and we only know a small bit of information. So let's look at one last example here. So in the diagram, GHJK, this rectangle, is similar to LMNP. And we want to find the area of LMNP. Now that's the bigger polygon. So we know the area of the original one. So we also know that if we're writing that proportion statement, I want to write my new over old. So I know that LMNP, so the area of LMNP divided by the area of GHJK should be equal to 21 over 7 squared. Well, 21 over 7 simplifies into 3, so that should be the same as 3 squared, which is 9. So the area, that proportion of the area should be 9. So if the bottom here is 84, so if we have 84 meters squared, and we're trying to figure out what this is, x meters squared equals 9. How can I solve for x? Well, I can multiply both sides by 84. And we can get x all by itself. And what we end up seeing is that the area of this other shape is 756 meters squared. So that is how we can use that property there. Now, again, some of the cool things we've learned today is that similar polygons have the same shape, congruent angles, and proportional sides. Because of this, we can actually use those ratios of the corresponding sides to determine interesting things. We can use it to find the measurements of different angles. We can also use it in situations like this. Now, we also know that those corresponding sides, or that scale factor of how we look at that, are related to the perimeter and area. So the proportion of the perimeters is the same as the scale factor, or the proportion of the sides. However, unlike that, the area of similar polygons, the proportion of the 2 areas is the same as the scale factor squared, or the proportions of the sides squared. So using these things, we can find a lot about these polygons, but we know that in order for them to be similar polygons, they have to have these properties. So to find if something's a similar polygon, it must have proportional areas that's equal to the sides squared. It must have proportional perimeters that's equal to the proportion of the sides, and the sides must all be proportional, and the angles must all be congruent. Once we know that, we know that 2 polygons are congruent to one another, or are similar to one another. Woof, that's not how we prove they're congruent. We know that they are similar to one another. If you have any questions, feel free to reach out, but that is how we can show that 2 polygons are similar.